Okay. Okay, I hope the slides are visible to all of you. Okay. So today we'll continue this module 2 on PN junction. So in last class, we basically tried to understand the fundamental equations which will eventually decide the overall terminal characteristics or the current voltage relationship of semiconductor devices. So we saw that there are equations like Poisson's equation, then electron continuity equation, hole continuity equation, and finally this current density, like hole current density as well as electron current density equation. So these are the equations we need to understand to calculate or to mathematically model the IV relationship of any devices. But since this is the first device that is PN junction device or PN junction diode, so that is why we gave this uh, mm, brief outline of the equations. So, but this is applicable for other modules also, like other semiconductor devices. So now we also gave just brief outline to the PN junction device structure. How does it look like, and what are the doping level and other things. So today we will try to understand the fundamental phenomena of PN junction diode or PN junction, any PN junction. Because see, unlike we know that we have this two-terminal device called PN junction, which is typically used to make current unidirectional. That means AC to DC or rectification purpose. But this PN junction again will encounter in bipolar junction transistor, where we have two back-to-back connected PN junction. So this PN junction is once again a fundamental building block of any semiconductor devices. So another important junction is, you know, that metal semiconductor junction. So that we'll see in the coming module. So this so this PN junction, first of all, from the previous discussion also, so this is not something like uh, we have one p-type material and another n-type material, and we are connecting them to get together, and then we'll get this PN junction. It is not something like that, because again, from the previous module knowledge, we know how to make one semiconductor p-type and how to make another semiconductor n-type. So this is by simply doping or incorporating foreign atoms, like in case of silicon devices, in case like we can dope it using boron, gallium, indium to get p-type, and we can incorporate arsenic, phosphorus to get n-type semiconductor. Now the thing is, to get this PN junction, this is not that we'll take one semiconductor, one p-type semiconductor, we'll take another n-type semiconductor, we'll simply connect them together and we'll get PN junction. So this is not the case, because see, the problem is, if we do so, because in some of the material or some of the emerging devices, sometime we need to or need to form PN junction like this. But the typical PN junction material is or PN junction diode or device or or junction we are fabricating simply by we are taking one N-type semiconductor, then we are incorporating P-type dopants. That means we have N-type semiconductor where we have silicon doped with, let's say, arsenic, and then we are implanting. This process is called implanting, typical to the same silicon fabrication process. So implanting means high energy this boron or aluminum or gallium atoms are bombarded from this top side, and then they will go inside this N-type semiconductor, and electrically this top behavior will change to P-type. So then this top layer now converted to from the N-type to P-type, because here the majority carriers will be your holes. So this way we are fabricating the PN junction, because see now here this is this junction, this interface is one side we have P-type semiconductor, another side we have N-type semiconductor. So once again, so here we are, this is not that we are taking two separate P-type and N-type semiconductor and connecting them together, or attaching them or gluing them somehow, and we are getting this interface. This is not true, because the problem, if we just simply connect this PN junction differently, so then the problem is that interface. Because again, in the metal semiconductor, this module will see, because in case of metal semiconductor we do not have any choice, but we need to connect metal with the semiconductor, because metal is different entity, semiconductor is entity, different entity. So in that case we simply need to take one metal and one semiconductor and then connect. So these two we need to connect. But in case of PN junction, remember the material is same, only the doping we are doing differently, and we eventually we are getting PN junction. But in case of metal semiconductor junction, we are simply need we need to take a metal differently, semiconductor differently, and connect them together. We will get metal semiconductor junction. Now the problem is, in last module, in the recombination part, if you remember, we mentioned briefly one point regarding the surface state or the dangling bonds. Because see, whenever we'll like, these are all, if we consider that three-dimensional PN junction, or this, let's say, one P-type material. So this is, let's say, a P-type semiconductor. So now this P-type semiconductor, this it has 6 surfaces, and all these surfaces has that unsatisfied bonds. That means that top silicon layer will have one dangling bonds, or the bonds which are not satisfied, because this another silicon we do not have at the surface. So all the surface atoms or the silicon atoms will not find another neighboring silicon atom to complete this covalent bond. So now the bond is called dangling bond, and this dangling bond will create the problem. So every time whenever we'll attach another material or another device or another material to this silicon, because this problem will arise in case of metal semiconductor junction, because here we do not have any choice, but we need to take a metal semiconductor differently and connect. So in that case, at this interface, there will be lot of these dangling bonds, and those dangling bonds will eventually create some surface states. So these are called surface states, and these surface states will create lot of unintentional problems. So anyway, this is a kind of one famous line in semiconductor device. So it is said that like bulk, because it has 6 surfaces. So semiconductor, the word, the inside this surface, the inside this semiconductor, all the other atoms are, so surface and bulk, to this component. So now it is said that the bulk is made by the god, while the surface is invented by the devil, because this surface will show different or unintentional this kind of behavior. And this is the problem we'll see, this dangling bonds related surface state problem will encounter if we connect this PN junction differently. But this kind of problem, this surface state problem, will not be there if we fabricate our PN junction in this way. So we take N-type semiconductor, then simply bombard with the different atoms, then the top layer of this N-type semiconductor is converted to P-type. So then there will be no this surface or this type of issue. Okay, so now uh, again, if you have any doubt, just stop me and let me know if you have any doubts. So now let us see. Okay, let us. But for this analysis or for understanding PN junction, we'll take P and N-type semiconductor differently, and then we'll try to understand all the PN junction this behavior. But in exactly in fabrication, we are not doing this. But for analysis, let us consider we have one P-type semiconductor, another N-type semiconductor, and they are not connected to each other. Now, in case of P-type semiconductor, we will have this, we know that acceptor dopants. So let me just quickly draw this. And in case of this acceptor, we have this all negatively charged ions, and donors, we have positively charged ions. And then we'll have carriers here, that means hole. Okay, another condition here is we have this semiconductor kept at 0 Kelvin, no temperature. That means all these dopant, these atoms are not ionized. So that means your this all these free carriers are still attached to the ions or these dopant atoms. So here we have acceptor dopants. So now these holes are attached to this. And similarly, in case of N-type semiconductor, the with the donor atoms, we have electrons attached because our semiconductor is at 0 Kelvin. There is no thermal energy to ionize these dopant atoms. So that is why it will look something like this. Now, what will be the band diagram? So if we want to draw the band diagram, again, these are not connected. So P and N, these are not connected. So now if we try to draw the individual band diagram of this P-type semiconductor and N-type semiconductor. Okay, so again, as we understand, like now onwards, we will simply show this conduction band bottom and the valence band top. So this is EC, this is EV, this is EC, this is EV. And where will be the Fermi level? This is some interesting question because this is at 0 Kelvin. So at 0 Kelvin, where will be the Fermi level? So because let us once again write this equation for our carrier concentration relating with the intrinsic carrier concentration and the energy level. So as we know or derived previously, so this is EF minus EL in case of N-type semiconductor, and similarly in case of PI semiconductor, it will be EI minus EF. Now the question is, where is the Fermi level at 0 Kelvin? So this is once again at 0 Kelvin. Where will be the Fermi level? Is this close to this conduction band or valence band? What will be the Fermi level? Because this is at 0 Kelvin. And at 0 Kelvin, all the electrons as well as holes are attached to its dopant atoms. So the Fermi level will be at the middle because they are not ionized. So there are no free carriers. There are no holes. There are no electrons. So the Fermi, this now from this equation you can see this EI will be equals to EF because this is again zero. That there is no carriers and electrons holes. So EF is eventually equal to the EI or the intrinsic carrier constant. Sorry, intrinsic Fermi level. So the Fermi level will be at the middle because this is at 0 Kelvin. So here will be our Fermi level. But still this based on the doping concentration we'll have the donor so sorry here we'll have the acceptor this energy level, but there is no hole or this carrier transition because this is at 0 Kelvin. But once again here we'll also have ED, but there is no carrier transition. So all the these electrons are at the valence band. There is no free carriers. But just to show, I am drawing this. So this is the acceptor level, this is the donor level. So this is the picture at 0 Kelvin and when our this P and N both are separated. Now the next this step to understand this PN junction behavior. Again, just for your information, this PN junction diode and this understanding is not very easy. Although this is the most fun, I would say, like basic device structure or junction. But what is exactly happening inside this PN junction? Sometimes we have a lot of confusion. So that is why I am going very slowly so that there should not be any confusion after this E311. So let us try to understand. So what is exactly happening and how this all the phenomena are related. So okay, so now these are two different. Should I continue here? Okay, maybe here we can continue or we can draw here. So now, if this P and N both are connected, what will be the behavior or what will be the your band diagram? Once again, I'll not draw the entire this junction. So then maybe few. And still it is at 0 Kelvin. If it is still at 0 Kelvin, then still these holes or electrons are attached to the ions. There is no free. This thing will get repeated here and here. Now, what will be the band diagram? Now we have connected this P and N type semiconductor, but still this is at 0 Kelvin. So again, we know that there will be one Fermi level, like any. So because this is once again whatever we are considering, this is under thermal equilibrium, or again this is here we do not even provide any temperature to the semiconductor. So this is absolutely at equilibrium at 0 Kelvin. So no temperature, no external energy. I guess someone's mic is not muted. Please mute it. So now we'll have band diagram something like this. So now our this P and N semiconductors are connected but at 0 Kelvin. And once again, this we know that under thermal equilibrium, inside any semiconductor, we will have only one Fermi level. So the Fermi level should be constant. So that is why this is a Fermi level, and then till this is at 0 Kelvin. Now let us start to heat up this semiconductor. So now I need to go to next slide. Now what will happen if we increase the temperature? Once again, I need to now in terms of carrier, what will happen? So few ions or few dopants will be ionized. So that means here will not have this electrons attached to this in case of N-type semiconductor, and similarly this in case of P-type semiconductor, the holes will not be attached to the dopant, this atoms. Now they are ionized. So few number of dopant atoms will be ionized. So when we have few numbers of dopants ionized, again now this free electron here in the N side and these holes will hit each other, or like see now, remember now this T greater than 0 Kelvin. So what is happening fundamentally? Fundamentally it is getting ionized, and at the same time, so let me write this. So one is this, now this electrons or holes which are free carriers, which can move within the crystal, they are free from its this donating atoms or this ion or dopant atoms. So that is ionization is happening. Another important thing happening, these carriers are getting thermal energy. So these moving carriers now have some thermal energy because now we have provided some temperature to our semiconductor. So this is now T greater than 0 Kelvin. So we have ionization, that means we have free carriers, and those carriers have some thermal energy. Thermal energy. And this thermal energy, if we keep on increasing, again from the previous module, this discussion, if we remember, this thermal, due to this thermal energy, this there is a random thermal motion. All these carriers will have random thermal motion. Random thermal. And due to this random thermal motion, this sum of this electron and the sum of this hole will merge. That means eventually they will recombine, and this ions, this here we have acceptor ions and the donor ions will be uncovered at this interface, because see in this at this close this boundary between your p-type semiconductor and n-type semiconductor, there is there it is more likely that we'll have this uncovering of ions, because there this electrons and the holes recombination, this probability is more. So, but remember, all these free carriers have this random thermal motion. So here we have a lot of these free carriers, and they have this random thermal motion. And at this boundary, So these electrons will see or will encounter these holes, and similarly these holes will encounter these electrons at this boundary or at the interface. So then they will recombine, and due to this recombination, these ions will be uncovered. And due to this, there will be some electric field. So as we know, because see here, these ions, okay, here once again I am repeating, in semiconductor, electrons and holes, they are the carriers, they can move, but these ions, these are fixed at the crystal, they cannot move. So this is, let's say, these are boron atoms. After accepting this electron or this donating holes, it becomes negatively charged. And similarly, this positive discharge, these are essentially fixed, let's say arsenic atom, so they are fixed in the crystal, they cannot move. And due to this immobility of these charges, so due to this immobility of these charges, there will be an electric field developed, and obviously the direction will be from this side to this side, because here we have positively charged donor atoms and here we have negatively charged acceptor atoms. So the electric field will be developed. Remember, if these ions can move within this crystal, just think, but then there will be no electric field developed. But these ions cannot move in the crystal because these ions are fixed to the semiconductor lattice or the crystal, they cannot move. So that is why, because they cannot move. And now we have population of negative charges in the p side and the population of positive charges in the n side at this interface of p-n junction, and we have this electric field developed. And we know that this electric field, this name of this potential is nothing but the built-in potential. But what is the role of this built-in potential? And and what will be the this width of this built-in this depletion width? This is also called depletion region because it is depleted of mobile carriers. Remember, this is depletion width in terms or considering the mobile carriers, because there will be charges. These charges are there, but this is depleted of mobile carriers, either electron or holes. That is why the name of this interface or this width is called depletion width. Now this depletion width again, we'll see all this once again in detail. So here we have depletion approximation. So there is a abrupt transition. So after this interface, there is some abrupt transition, because we'll see there is a not exactly abrupt transition, but there is exponential decay in this charges. So we'll see how and why it is happening in the coming lectures. So but there will be approximation, and then there will be depletion width. Let us quickly see the now the band diagram. What will be the band diagram? Once again, this is still under thermal equilibrium, so that means one thing will remain constant across the p-n junction, so that is the Fermi level EF. So now this is p type, maybe we can take, now this is p type, so we'll have so here we have this p type, that is why once again Fermi level is closer to our valence band and far away from our conduction band, because this is a p type. Again, this is not exactly the same, but So this is the depletion region. Once again, this is inside where Fermi level is closer to conduction band and far away from the valence band. And here, now due to so thermal energy, due to the thermal energy, because here our now the condition is T greater than 0 Kelvin, and let's say still it is still it is less than the room temperature. So we have this temperature condition. Again, overall, this phenomena we will observe under thermal equilibrium. So whatever the discussion we are now doing under thermal equilibrium. Now, under this temperature condition or this thermal equilibrium, the carriers in the both side, there will be carriers, and those carriers or those electrons and the holes will have random thermal motion due to the thermal energy. And now the question is, just we have discussed that due to the thermal energy, these electrons from here will cross this interface, will meet these holes, and then there will be this depletion region. Now, how long this process will continue? Once again, the question is how. So let's say here also we'll have some electron. Will this electron be able to cross this interface and meet another hole here, or this hole will be able to jump over this build depletion region and meet another electron here, so that will be have more uncovering of ions, and then depletion with WD will keep on increasing. So if will this keep on happening, or when it will stop? Like, what is the condition? We know that there is so this thing cannot happen. Like this process cannot continue infinitely. This recombination. See, electrons has the thermal energy, holes has the thermal energy. They are meeting to each other. Then depletion region is continuously increasing. This thing cannot continue forever. So at some point it must stop. What is that condition? Okay. So remember okay, I'll come to that. So what is that condition? How long it will happen, and when it will stop, and when this WD will be fixed, and this electric field and other things will be fixed. So the thing is, can I draw here? Now the most important part of today's discussion. See, once again, let us try to draw the distribution, electron distribution in the conduction band, as well as the hole distribution in the valence band. Why? Because see, again in the previous module we have calculated this electron this concentration in the conduction band by combining this Fermi statistics as well as the density of states, by multiplying and integrating above the energy level, some energy level. We have calculated the number of carriers which may be available above in the conduction band, and the number of carriers which may be available in the valence band. Now again, if we consider that our semiconductor is at relatively higher temperature, that means if our semiconductor is 3 kT high temperature, and 3 kT this temperature is considering this temperature, room temperature, even if we consider, it is around 75 millielectron volt. So this is very small. And why we are considering this 3 kT? Because we know that if we consider this our energy, this all energy level above 3 kT, then that Fermi direct statistics or the Fermi function we can approximate as a Boltzmann constant or Boltzmann distribution. So if we do that, if we consider that our energy is more than 3 kT, and then if we consider this Boltzmann distribution, then our electron concentration distribution above the conduction band will be something like this. So this will be the carrier. So this is the energy, and this way, like this is the energy increasing, and this is the number of carriers. So if we keep on going above this conduction band, so then the number of carriers will keep on decreasing. So these are something which we have already seen in the last module. So how the distribution of your density of states and the distribution, Fermi direct distribution, will decide this kind of distribution in the conduction band. So we have this electron distribution. That means if we go top in terms of energy, if we move top above the conduction band, the number of electrons will decrease. The number of electrons will decrease exponentially, because this is a Boltzmann approximation. So if we consider this Boltzmann approximation, this number of electron concentration above the conduction band will decrease exponentially. So now this all electron has the thermal energy. So here we will have electron. So we have so many electron. Now which electron will go to the inside? So whatever we are discussing, like still we have electrons here, holes here. So will they cross this depletion region and meet this another electrons or holes? What is the condition? So that's now in terms of band diagram, see only the electrons here. That means the electrons which has energy higher than this. So the electrons which will be here, because it has a higher energy. So this electron can cross this depletion region and can go to P side. Once again, see here we have so many electrons. This only the electrons which has higher energy than this potential barrier. This is also called potential barrier. So this electron can go to the P side, and now the rest of the electron will simply bounce back, will not be able to cross this potential barrier. Again, from where this energy is coming from, or these electrons, this is all thermal energy. So that means these electrons are hot enough. So these electrons are hot enough, or it has sufficient thermal energy so that it can cross this potential barrier and go to P side. And similarly, if we look at this your P side, similarly we will have this we will have this kind of distribution of holes, and again holes only the holes which are here, so they will be able to go to inside, but rest of the holes will bounce back. They will not be, because again we know that here this electron and the hole has different behavior, and if we keep on increasing the energy, so the hole in so whenever we will increase the energy, or so then hole will go downward and the electron will go upward, because overall this energy band diagram is the energy of electron. So that is why if we increase the energy of this system, so the this electron energy will increase and the hole energy will decrease. So that means the holes which will have higher energy, so they will be able to go to your inside and cross this depletion region, but rest of the holes which will not have sufficient energy to cross this potential barrier, they will return back. Okay, so this is now what is this thing, what is happening? See, very simply, because I know sometime you can when I took your Viva in as a part of IC161P, or I have seen like there are a lot of other concepts like this they are coming merging, so electrons are repelling, something like that. But fundamentally, here we are having this energy of free carriers, random thermal motion of carriers, and due to the random thermal motion, the carriers are moving. Again, this random thermal motion, again, if we refer to our previous this discussion, that is why I spent more time on the module 1. This is also called diffusion, isn't it? Because because in diffusion also, like this diffusion of carriers, the carriers from the higher concentration to lower concentration, it will move, and this movement is due to the thermal energy. From where it will get the energy? This is the thermal energy, and that random thermal motion, that random motion is there, and this is coming from the thermal energy. And similar thing is happening here. So this is also your diffusion. So this is nothing but the diffusion, which is due to the thermal energy of the carriers. Now, which process will stop this? Because see, here we are having this electrons going from here to this holes moving from p side to n side, and the electrons moving from n side to p side. So again, this process, once again, this is under equilibrium. So there should not be any current. So this is thermal equilibrium. So there should be some opposing process which will cancel out this current. The current due to the diffusion of electron from the n side to p, the current due to the diffusion of holes from p side to n. So which process will cancel out this current or this diffusion related current? So the process is, here we'll have, let me take another color, maybe. So due to this thermal energy or the higher temperature, so we'll have electron hole pair generation and primarily within this depletion region. So here we'll have hole and we'll have electron. This excitation, we could have this electrons moving from the this valence band to the conduction band, and this is within the depleted portion. Remember, this is the depletion region. In this depletion region, there should not be any carriers, because this is depleted of mobile carriers. Now, whenever we'll keep our this semiconductor at greater than 0 Kelvin temperature, there could be this electron hole pair generation within the depletion region. And now, see, whenever we'll have this one electron excited to your conduction band, what will happen? So this electron will move this side, because this electron will always try to take the lowermost energy. So this will go this side, and similarly this hole will always try to take lowermost energy. That means it will move this direction. Now see, this electron is going this direction from right to left, and this electron is going from left to right. And similarly, we have this hole moving from right to left, and this holes moving from left to right. This way, and this is what is happening, and this why this electron and the hole is moving this direction and this direction. This is due to the electric field or the built-in potential, and this built-in potential arises due to these immobile charges, and we have this band bending. And this process, this is called the drift, because here these electrons, this red color, this electrons movement, this electron holes movement is due to the drift. But this electron movement, this is due to the diffusion. Now see the fundamental carrier transport mechanisms, how they are involved in this PN junction. So this there is a diffusion due to this thermal energy of carriers, and there is this drift due to this built-in potential, and now these two will cancel each out, and that is why we will not get any current out of this under equilibrium. So under thermal equilibrium, there will be no current. So this electron motion will cancel out this electron motion, and this whole motion will cancel out this whole motion. So drift diffusion cancel out, drift diffusion cancel out. So now quickly let us, what is the time? Quickly let us calculate the built-in potential. Just try to quantify what will be the built-in potential. And for that, we need to quickly draw the EI. Any question, any doubt, please let me know, because this is very fundamental. So this is the EI, intrinsic energy level. And now if we, so this is called, so this is the energy difference between the intrinsic level and the Fermi level in the piece, and this in the Fermi level in the N side, and it quantifies the doping level. So as we know that this higher will be this energy, so higher will be the p-type concentration, and higher will be this energy, higher will be the your n-type concentration or the electron concentration. So now if we quickly try to quantify this built-in potential psi naught. So again, let me, this q psi p, that means this, and here this is a potential to, if you convert this to energy, because all these are energy term EIEF, so then q psi p is nothing but EIP, that means intrinsic energy level in the p side, sorry, and minus EF. And this EFP, we know that in previous slide we mentioned that equation P equals to Ni exponential EI minus EF by KT. Okay. So now whenever we'll increase the temperature, so first all the dopant atoms will get ionized, because again we know that that EA energy level and ED energy level is very close to your conduction band and valence band. So the electron and the hole will move easily from that energy level. So that is why, so the number of holes is almost equivalent to the acceptor dopant atoms, so Na. So now if we take this help of this equation, and here if we mention this, it will be Kt natural log of Na by Ni, and similarly your Q phi n, Q phi p, Q phi p, oh sorry, n will be Kt natural log of Nd by Ni, and from here you can guess this overall, this your built-in potential, that means this total potential barrier Q phi naught is equals to the summation of these two, which is again, just if we write this potential, now we need to divide it by the Q natural log of Na Nd divided by Ni square. So this is the potential or the built-in potential. And Now we have also understood that there will be this balancing of this diffusion and drift of carriers, both sides, like for the both for holes and both for the electrons. Now let us try to just quickly discuss how we are getting the current and why the behavior is like we know that our p-n junction this IV characteristics sorry, behavior is something like this. Why this is coming and how this is coming. So if we forward bias this p-n junction, I think we need to. Okay, let me go to next slide. Again, now we are moving to non-equilibrium condition. We are biasing our this p-n junction. Let us forward bias it first. So if we forward bias, so once again we'll have this depletion region here. So what will happen in case of this band diagram? So now this band diagram, I am not drawing now the Fermi level because Fermi level will no longer be constant because this is not now under thermal equilibrium. So there will be no constant Fermi level. So there now Fermi level will split. So now in terms of that, this carrier flow or the diffusion or drift, if we see now we have applied forward bias. So let's say earlier we had this conduction band here and valence band here, and due to the application of forward bias VD, now this built-in potential reduced to here. Like earlier this was the potential barrier. Now due to the application of your forward bias QVD, now this is reduced to here. The potential barrier decreases. Now in terms of this carrier distribution, what is happening? That is important to understand the current. So once again our this electron carrier concentration will be something like this. Now see, these many carriers earlier were hot enough to cross this junction. Let me take different. So these many carriers were hot enough to cross this junction, and that were those were eventually balanced out by those drift or thermally generated. That is thermal generation. Okay, those carriers that thermally generated carriers within the depletion region. Now due to this forward biasing, now more electrons. See this now this electron here. These additional electrons will be able to cross this PN, this barrier, potential barrier. So this is the overall carrier concentration or electron concentration profile above EC, conduction band. Now due to the application of forward biasing, our this potential barrier for the electron reduced, and due to the reduction of this potential barrier, now more number of electrons will be able to cross this potential barrier or this depletion region. And similarly, in case of your these holes, so let's say, so earlier, let's say these many holes were able to cross. Now, due to this barrier lowering, this additional these many holes will be able to cross. So now this is again what is happening and why these are able to cross. Now the energy due to which these electrons are crossing, this is the random thermal motion. Fundamentally here we are having diffusion. because here we have having higher this thermal energy of carriers, and holes are large in number, and it is diffusing towards this inside. And similarly the electrons, here it has the thermal energy, enough thermal energy, and due to the diffusion it is crossing this potential barrier. Only remember these two phenomena, this diffusion and this drift. There is don't consider any other thing, because in this way it will be very easier to understand and remember, and eventually this is what actually happening inside these devices or inside this PN junction. Now quickly, if I uh, write this, uh, how many electrons and what will be the current. See, this was before your this forward biasing. So this was the potential barrier psi naught. So again, if we recall from our previous module, we calculated that how many how many electrons or the carriers will be there above energy q psi naught. So this thing we have seen in case of Fermi-Dirac distribution, that discussion. So then the current or the number of carriers will be proportional to e to the power minus q psi naught by kt. This is before the forward bias. Now after forward biasing, this is the additional number of electrons they will be able to cross this. So what is this additional number of this electrons which will be able to cross this potential barrier? This is proportional to e to the power minus q psi naught minus q, okay, we have q Vt divided by Kt. So this is the additional number of carriers which will be able to cross this. Okay. Now what will be the net flow? Net flow means a net flow due to this forward biasing. So net flow means this was the electron crossing before, and now this is the additional electrons crossing. And now what is the additional number of electrons crossing due to this forward biasing? That will be the net flow, and this net flow will eventually give us the current, and which is proportional to e to the power this q psi naught minus Vt by Kt minus this q psi naught by Kt. Now if we just see this, e to the power q psi naught by Kt divided by q Vt by Kt minus 1. So this is nothing but your diode equation, you know. Now if we write in terms of current, and if we consider this, there is this proportionally constant Is, so this is the current equation we all perhaps seen. So this is the current equation. Now see how this is coming. So just final word or this take home message from this today's discussion is that there is a drift, there is a diffusion, and this diffusion is due to the thermal energy or random thermal motion, and this drift is due to this built-in potential, because this electron they will come down and this hole will go up. And now, but just by changing, just by increasing or decreasing this barrier height by application of forward external biasing, we can increase and decrease the number of carriers crossing this potential barrier. Once again I am telling. So what is happening? So another comment, just quick comment. See this, whenever you will see this term Kt for any device equation, they are all thermal device, because that device is governed by the temperature. So eventually this PN junction and other this device where we'll see this Kt term, so this T is there. That means these are all thermal device, and that thermal process, or the process which is due to the thermal energy, that is deciding the current voltage characteristics or the eventual terminal characteristics. And here it is coming in this way. So here we have this carrier concentration, electron concentration in the p inside, hole concentration in the p side, and just by applying the forward bias or reverse bias, this how many electrons or the holes will cross this barrier, that we are deciding. We are not giving some external energy to matlab, overall, see, we are not giving any energy external, that this Vd is not the energy we are providing to the electrons and the holes. Using this Vd, we are simply lowering or increasing this potential barrier, and the movement is due to the thermal energy. This movement, due to which these electrons and holes are crossing this barrier and eventually giving us that diode current, it is due to the thermal energy. This is the overall take-home message. So this Vd, external bias, we are increasing, decreasing potential barrier, but the current or the flow of carriers is due to the thermal energy. Okay, so I'll stop here. It is already one. So please do let me know if you have any doubts. I'll continue this thing once again in the next class. Any question, any doubts? So, okay, so if there is no more question, thank you. I'll encourage questions from your end, because see, sometimes it is anyway, it is difficult to understand whether you are getting this or not. But please do let me know if you have any doubts.